Hi there. We're going to be continuing on in section 4.1 today. We'll start off with a little bit of vocab. Some of it will be review, some of it will be new. I do believe this first one is probably new. A differential equation, even though we worked quite a bit with them in the first part of this section, we didn't really call them that by name. But a differential equation is an equation given as a derivative. It's that simple. So when they're telling you, hey, f prime is x, so what's f? And you anti-differentiate to get the answer, you are solving a differential equation because the original equation that was given to you was, in fact, a derivative. To solve a differential equation is to find the equation that is the antiderivative of the differential equation. And again, that's what we were doing yesterday, and we will continue to do today. A general solution to a differential equation is one that contains a plus c term at the end of it, also known as a constant of integration at the end of it. And those are the kind of solutions that we were finding yesterday. An initial condition, this is a new phrase perhaps, it's an ordered pair through which the solution passes. It can be used to determine a specific value of c. So if they give you some information such as, oh, by the way, when x equals 4, f of x equals 10, you can go in, plug in 10 for f of x, 4 for x, leave your plus c in there, and then solve for c and get an actual, what they call, particular solution. A particular solution to a differential equation is one where the constant of integration is known. It's a specific number. That's the kind of solutions we're going to be looking to come up with today. There is no one single graph for the general solution to a differential equation. For instance, if I know the derivative of y with respect to x equals 2x, I can kind of figure out what y is. I'd have to integrate it. Integrating dy over dx would leave me with y, and then integrating the right side would give me x squared plus c. Now, if I tried to graph this x squared plus c, this x squared plus c is my general solution. If I tried to graph it, let's say I could say, well, what if c is 0? Then I get kind of your standard parabola. But if c is like -3, then I'd have that parabola shifted down 3 units. And then I'd have this. That's pretty terrible. If c were like +5, my vertex would be here. You know, then I'd have something like this. So there's infinite solutions here depending on what c is. They all kind of look the same. They're all copied and pasted versions of each other, but there's no one specific solution. Now if we were to go and say be given this one little simple hint, if we knew that y of 1 equaled 3, we could say, all right, well, if y of 1 equals 3, that means it's got to go through the point 1, 3. I'll make this one red. Well, that means there's got to be symmetry, so it's also got to go through this point, and then the vertex is right here, and we go up 2 and up, or right 2 and up 4. Then we'd have this would be a particular solution, and the only reason we can come up with that particular solution is because we were given this, which is what's known as an initial condition. So a couple of examples here. We want to find the particular solution to this g prime of x equals 4x cubed plus 2. So since we're given an equation in terms of a derivative, that is therefore a differential equation. We can solve a differential equation first by getting a general solution that has a plus c term in it. And then since we're given this extra piece of information here, this initial condition, we should be able to figure out a specific value for plus c and therefore get what's known as a particular solution. So let's start by tackling this function g prime. If I want to get from g prime to g, I simply integrate g prime, because integration and differentiation are inverses, really. Integrating 4x cubed is going to leave me with 4, and then x to the 4th over 4. The 4 gets pulled out as a constant, and then x cubed becomes, if you follow the up a power over that power rule, you get x to the 4th over 4. Integrating 2 will give me 2x with a plus c at the end. This is g of x. I can simplify this, of course, to just x to the 4th plus 2x plus c. Now, since I know that x is 1 when y is negative 3, I can plug in negative 3 for my y value, or my g of x value, and I can plug in 1 for my x values, which would give me 1 to the 4th would be 1, 2 times 1 would be 2, plus c. And as a result, I can tell, let's see, if I subtract 3 from both sides, I'd end up with a negative 6. Now, I have all the pieces of information that I need. I just have to write the actual equation. So I'd have g of x, as my final answer, would equal x to the 4th plus 2x. And instead of plus c, I'm going to put minus 6. That, with a specific value of c filled in, is my particular solution. All right, one more example here. They're a little more evil here. They're giving us h double prime and asking us to get all the way back to h. So I can at least get from h to h prime by differentiating the second derivative. Notice, again, I'm using things people forget a lot. I'm using parentheses because I actually have two terms in my integral. I'm also using a differential because, quite frankly, you're supposed to use a differential every single time you write an antiderivative or an integral. If I work this problem term by term, anti-differentiating 3t will give me 3 and then t squared over 2. Anti-differentiating negative 1 will simply give me minus t. We still have our constant of integration. So this is not even a general solution for h yet. This is still h prime. I can figure out what this value of c is. Since I'm at an h prime level, I'm going to use the initial condition that's given to me for h prime. Make sure you're using apples with apples, or I don't know, use dog food with dogs and cat food with cats. I don't know, some dogs will eat anything. But I can plug negative 1 in for my y value and then 2 in for my t value. I get 3 times 2 squared over 4, which is 2, minus t is 2 plus c. So here c would have to equal, let's see, 6 minus 2 is 4. Subtract the 4 from both sides. Negative 1 minus 4 is negative 5. So h prime, I have a particular solution for h prime, which is 3 halves t squared minus t minus 5. There we go. All right, so we still need to get to h. So we need to integrate. Oops. We need to anti-differentiate h prime. To go one more derivative up the food chain. So 3 halves t squared anti-differentiates to 3 halves t cubed over 3. t anti-differentiates to t squared over 2, and 5 anti-differentiates to 5t. H of 0 equals 4. Okay. So this is H. Oh, they gave us 0 for t. Thank you. All right, so that means when I plug in 0 for t, I should get 4 for h. And the nice thing about a polynomial function is that when they give you the independent variable equaling 0, you are basically getting told exactly what c is. Because if I plug in 0, that's gone, that term's gone, that term's gone. There. So all I have to do now is clean up some of the algebra here. I get t cubed over 2, or 1/2 t cubed, minus t squared over 2, minus 5t. Instead of plus c, I'm going to say plus 4. And that would be the particular solution for h. So yeah, the only difference between yesterday and today is that once you get your general solution, you just need to plug in the x and y values that you are told for your initial condition so that you can actually tell what c is, thereby getting a particular solution. Have fun.